Welcome back to the engineering lab. Look, I am absolutely thrilled you're joining me for this explainer today because we are tackling a massive, massive roadblock for so many students. We're talking about a hurdle that trips up even the best coders. Cambridge principal examiners have explicitly reported that decomposition, specifically the art of breaking complex problems down into smaller, manageable subproblems, is one of the single most misunderstood areas in the entire computer science syllabus 9618. Think about that for a second. Students all across the globe are literally leaving incredibly valuable marks on the table, not because they don't know the tech, but because they don't know how to demonstrate their thinking. But hey, here is the good news. We are going to fix that right now. We're going to completely decode what examiners are actually looking for when they test your algorithmic thinking. So let's dive right into this. Here is our roadmap for today's explainer. We'll start with number 1, the challenge. Then move to 2, the strategy reveal. 3, the transformation. 4, we'll do an interactive workshop. And finally, 5, we'll give you the final system. All right, let's kick things off with section 1, the challenge. Specifically, we're looking at decomposition pitfalls. We need to start with a very real, very honest look at why candidates drop marks when breaking problems into subproblems. You see, it's almost never because they don't know how to code. It's not because they don't understand what a subroutine or a function actually is. Across all the syllabus codes, 0417, 0478, 0983, 0984, 2210, and especially the incredibly rigorous 9618A level, the challenge is almost entirely about how candidates articulate their problem-solving process on paper. I really want to ask you this central question to get us in the right mindset. Why do students find evaluating algorithm efficiency so hard? Just take a second and think about your own experience in the exam hall. When you're sitting there, the clock is ticking down, and you are asked to evaluate the efficiency of a newly decomposed module, do you freeze up? Do you just kind of guess and hope for the best? The hard truth is, it almost always comes down to flawed execution on exam day, rather than a lack of raw technical knowledge. You know the concepts, but applying them under pressure against that ticking clock to a completely novel scenario, that is exactly where the friction happens. Let's look at 2 hypothetical students taking the exact same Cambridge exam paper. On the left side of your screen, we have Alex. Now, Alex overloads their answers with raw computer science facts. If the exam question is asking about a specific payroll system, Alex writes down a perfect textbook definition of top-down design and modular programming. Sounds good, right? Wrong. Alex completely misses the deep analysis of that specific payroll scenario. Because of that, Alex gets 0 marks for context. It's harsh, but it's true. Now, on the right, we have Sam. Sam rushes through the paper. Sam looks at the code but completely misses the specific command word requirements. For example, if the question explicitly says evaluate, Sam just describes. These are classic mistakes. The Cambridge assessment framework prioritizes analytical depth over superficial breadth. Showing off the breadth of your knowledge won't get you an A-star. It's the depth of your analysis that secures the top grades. Moving right along to section 2, the strategy reveal. Let's open up the examiner playbook. It is officially time to pull back the curtain. We are going to look at exactly how your logical reasoning and systematic analysis are graded by Cambridge examiners. Grasping what we call the method mark strategy is a total paradigm shift for most students. This Cambridge assessment principle explicitly states that marks are awarded for the process and the systematic deconstruction of a problem, not just the final coded answer. They want to see the gears turning in your head. They want to see your step-by-step algorithmic thinking. If your final output is slightly off because you made a tiny, minor syntax error, but your decomposition into subtasks was perfectly logical, clearly documented, and well-reasoned, you are still going to secure the vast majority of the method marks. Remember this, the examiners are grading your brain's internal compiler, not just the final output on the page. So the absolutely crucial point here is captured in this exact benchmark, which is pulled straight from the syllabus guidelines. It reads, top-performing students exhibit connected, conceptual understanding transferable to unfamiliar contexts. I really need to let that sink in for a second. Unfamiliar contexts. When you open that exam paper, you are going to see a system you have likely never seen before in your life. Maybe it's a completely bespoke drone navigation system. Maybe it's a highly complex hospital triage database. Context is quite literally everything. If you just provide generic textbook answers about what decomposition is, without actually applying it to that specific drone or that specific hospital, you are going to instantly lose marks. So, how do we guarantee we hit that context every single time? We use the Peel framework. Top students structure their answers sequentially using these 4 steps. First, the point. You state your specific technical argument clearly. Second, evidence. You pull data or code snippets straight from the provided scenario in the paper. Third, explanation. You detail exactly how your technical point applies to that specific evidence. And fourth, the link. You tie it all back directly to the command word used in the question. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE, to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's see how we actually apply this framework to transform your answers. That brings us perfectly to Section 3, the transformation. How we take failing responses to the top tier. Let's look at a classic critical analysis question. A massive error students make here is identifying similarities only. They'll look at two sorting algorithms or maybe two subproblems, and they'll just write, they both use loops, and they move on. That is totally incomplete. The examiner-approved method requires identifying similarities and differences, and doing so using comparative connectives. We're talking about words like whereas, conversely, or in contrast. True comparative analysis requires both sides of the argument to be supported by evidence pulled straight from the text, which allows you to draw real conclusions about their relative importance. Applying this simple shift, that is exactly how you turn red pen marks into green check marks. To achieve that level of detail consistently without panicking, you need a reliable pipeline. This right here is the deconstruct, solve, evaluate pipeline. First, identify the given information. Literally underline the constraints in the text of the exam paper. Second, break it into logical steps. This is your actual decomposition. Third, solve systematically using the appropriate data structures. Fourth, check for reasonableness. Stop and ask yourself, does this output actually make sense for this specific scenario? And fifth, make justified recommendations. Listen, each one of these precise changes adds specific marks to your tally. If a question is worth 5 marks, imagine each bullet point on this slide seamlessly ticking off one of those marks. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE, to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's get into Section 4, the interactive workshop. It's time to lean in and test those skills. Imagine a 60-second timer counting down on your screen right now. We're looking at a complex computer science data table. Column 1 gives us a binary representation, column 2 requires a specific calculation step, and column 3 needs your output and evidence-based conclusion. Your challenge during a rapid data scan like this is to extract the core trend from these binary inputs before time runs out. Now notice how setting it up this way literally forces you to perform step-by-step decomposition. You simply cannot jump to the final conclusion without explicitly showing the calculation step. Why? Because the calculation step is your evidence. This is exactly how practicing practical application develops your programming and your analytical skills simultaneously. Now let's do a quick find the flaw challenge. Look at the text comparison right here. On the left is a highly flawed paragraph, completely lacking boundary checks. It describes an algorithm pretty well, but it completely forgets to address what happens if a user inputs a 0, a negative number, or just leaves a field entirely blank. The examiner commentary on this kind of flawed text is brutal, guys. It loses marks specifically for a failure to evaluate performance and efficiency under extreme conditions. Now look at the right. We have a perfect Peel paragraph. It explicitly tests the edge cases. It states the point. It uses the edge case as its evidence. It explains exactly why the algorithm might fail under those conditions, and it links it perfectly back to the required system reliability. This right here, this is what top-tier algorithmic thinking looks like. Finally, we've arrived at Section 5, the final system. This is your actionable blueprint. Let's bring all this theory into one place. Here is the definitive 5-step procedural framework you must use the absolute moment you open your exam paper. I want you to really notice the action verbs here. First, deconstruct the question. Physically circle those command words. Second, extract relevant data. Isolate the exact constraints of the system they gave you. Third, select your analytical framework. Decide right then and there if this is a time complexity issue, a data structure choice, or a modular design problem. Fourth, execute with clear notation. Write out your pseudocode or logical steps as cleanly as possible. And fifth, present with correct terminology. Do not use informal slang. Use precise, Cambridge-approved vocabulary. But look, even with that amazing framework, you still need to watch out for the pitfalls. I want to heavily warn you about these top 3 mistakes pulled straight from Cambridge Principal Examiner reports for syllabus 9618. Mistake number 1,
vague answers lacking specific technical details. Don't just generically say it's faster. Say it reduces time complexity to a logarithmic scale. Precision matters. Mistake number 2, forgetting to check boundary conditions in edge cases. An algorithm isn't robust until it handles bad data gracefully. Mistake number 3, the classic error, providing generic answers not specific to the question context. Remember, if you don't link your answer back to the specific scenario provided in the exam, you are literally throwing away your grade.
So, the big question is, how do we actually remember all of this under intense exam pressure? Well, here is a really powerful memory hack. Create a custom acronym using the first letters of those 5 procedural framework steps: deconstruct, extract, select, execute, present. D-E-S-E-P. DCEP. Lock this into your brain right now. I want you to write DCEP right at the top of your scratch paper the absolute second the exam begins. Having that visual anchor ensures you never freeze up during the critical analysis phase.
Now, why are we focusing so intensely on this systematic approach to decomposition? Because the raw data proves that it works. Students who implement these specific computer science strategies, who truly master the PEEL framework and the DSCEP pipeline, see an average improvement of 2 full grade boundaries. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos.
Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.
Before you go, I want to leave you with this final provocative thought so you can instantly apply your new rigorous algorithmic thinking. The next time you sit down to practice, when you face your very next decomposition question, what is the absolute first boundary condition you will test? Think about it, plan for it, and execute it. Keep studying smart, keep breaking those complex problems down into manageable pieces, and I will see you in the next explainer.